Hello and welcome to EMI mitigation techniques for wide-bandgap devices. My name is Jared Quenzer and I am an applications engineer at Würth Electronics with a technical focus on electromagnetic compatibility and power. I have a background in EMC for conducted and radiated emissions, designing transformers, and also designing common mode chokes. We will start by talking about the benefits and drawbacks of wide bandgap devices, then discuss some practical applications to mitigate EMI for both conducted and radiated emissions. To make sure we all start out with the same fundamental knowledge, I'll start with the basic explanation of wide bandgap devices. Wide bandgap devices, or WBDs, as you'll see throughout this presentation, refers to transistors that use material with a wide gap between the valence band and the conduction band, like the picture shown on the right, over here. Two of the main technologies are silicon carbide and gallium nitride. Silicon carbide has the advantage of lower switching losses, higher power density, and higher temperature compared to silicon technology. Commercially available silicon carbide transistors, at least the last time I looked, achieved 1700 volts from drain to source and over 2000 watts of power. Gallium nitride, or GaN, has even faster rise times, but the transistors that I found recently are limited to 900 volts drain to source and around 175 watts of power. One of the reasons for choosing a wide bandgap device is to use higher switching frequencies to decrease the size of the magnetics. However, when you use higher switching frequencies, there are some drawbacks because this pushes the spectral energy into the most difficult section of the conducted emissions band. The examples that I have over here are with the limit line for conducted emissions, and this is just an example of a switching frequency of 150 kilohertz, second harmonic, third harmonic, fourth and fifth. You can see that this has a value of 50 dB microvolts, and it's technically passing. The third harmonic is close to the limit line, but in this example it is passing. When we shift that switching frequency higher, in this example, all I've done is take the same peaks and then just shift them over to a fundamental switching frequency of 500 kilohertz. You can see that now this peak, the fundamental switching frequency of 50, is over the limit line, and the third harmonic is actually fairly close. So just by increasing the switching frequency, I cause myself more issues. And this is just with the current EMC standards, because in the future, they might consider lower limit lines due to the ever-increasing amount of devices occupying the same electromagnetic spectrum. Most of the reference designs that I've seen either do not show EMC test results or do admit that making a wide bandgap device power supply that passes EMC is difficult, attempt a good layout, and still not have it pass the first iteration. Besides the higher switching frequencies, another issue is the fast rise times. These rise times dictate the envelope for higher frequency harmonics. This is based on the theory of Fourier series, where in this example, we have a sine wave and we have a square wave. And the goal of this is to create a square wave by imposing many sine waves at different frequencies on top of each other. So you can see as we add these sine waves with higher and higher frequencies, we get closer and closer to a square wave. This basically dictates what the envelope is of the spectral energy in the frequency domain. So there are two main points to consider here. One point right here, which is defined by your switching frequency or your period, TP, is where you start to have a 20 dB per decade roll off until this other point, this other important point, which is your rise time, TR, down here. This is where you start a 40 dB per decade roll off. So a good example for this is when you have 100 nanosecond rise time, this point over here is around 3 megahertz. When you have a switching frequency of 10 nanoseconds, so you increase this by a factor of 10, it shifts that point out to 31 megahertz. So now we effectively have more spectral energy to deal with, because instead of having this 40 dB per decade roll off on our side with all the harmonics hopefully staying within this envelope, now we shifted this point out further, higher in frequency, so we have more spectral energy to deal with. This is one of the main reasons there's a rule that you've probably heard for EMI, that fast changes in voltage, dVdt, or currents, dIdt, are the enemy when designing for EMC. So to combat this, you must have loop areas that are small and traces that are thick to minimize the inductance of the PCB traces. One technique that I've seen used is to use a larger gate resistor to slow down the gate. This does accomplish reducing the rise time and therefore shifting this point lower in frequency and making it easier to mitigate the EMI. However, when you're spending more money to buy a silicon carbide FET just to slow the gate down because you have EMI issues later on, doesn't really make sense, because you might be switching it at about the same rise time as a silicon FET, and you could have just stayed with the silicon FET and saved yourself a lot of money. Other things to keep in mind are your parasitic capacitances, especially due to PCB layout. Even with a good PCB layout, filtering will likely be necessary. So I'll go into some of the techniques that you can use to get rid of this noise. The first, starting with conducted emissions. The conducted band is from 150 kilohertz to 30 megahertz. Most of the noise in this band will be differential mode, and this can be filtered by using multi-stage low-pass LC filters to target various frequencies. For example, you would have a pair of LC, inductor and capacitor, for low frequency, another for middle frequency, and another for high frequency. So by having multi-stages, you can filter out most of the frequencies. This is an example of that. So if you have a problem frequency of 100 kilohertz, you want to choose a cutoff frequency of at least 1 decade below the switching frequency to make sure that by the time you get to this point, you have at least 20 dB of attenuation. Of course, because this is a low pass filter, then anything that's higher than that frequency will also be attenuated as well. Some common mode chokes, like this one pictured below, do include some differential mode attenuation. This is the graph for this part over here, showing the common mode and differential mode attenuation for all the different parts in this series. You can see that most of these have 100,000 ohms or even 1 mega ohm of impedance in both common and differential mode. So if you have a problem with both, this might be a good option to consider. And of course, like I had already talked about, there is still some common mode noise that you'll see in the conducted band, and this can be attenuated by using common mode chokes. So now let's do some testing. Here are some baseline measurements that I did using a 2-port listen so that I can separate out the differential mode noise and the common mode noise. And this is measurements that I took myself using our own internal test board that used a Cree silicon carbide FET. On the left, you see the differential mode noise. You can see it's way above the limit line. In this case, it's about 82 dB microvolts for the fundamental switching frequency. This fundamental switching frequency of the FET is 500 kilohertz. I did that to mimic the example that I was talking about earlier. Second harmonic, third harmonic, fourth harmonic. You can see basically all of these harmonics are above the limit line. Common mode, even in the conducted band, we do have common mode noise. And we do even have it at these peaks. Most people wouldn't think that. They would think that it would be an entirely differential mode issue, but you can see that due to the parasitics on the board, you do get some common mode noise as well at these same peaks. Of course, overall, the base of this is much higher because there's other circuitry on this board which is affecting that and causing all these other peaks up in this 10 megahertz range. So let's try and filter this noise out. I'm going to use the Design Your Own EMC filter kit. And this is just a nice board to have with a bunch of different components inside of this box so that you can design your own line filter. You have everything you need in that box. Starting off, we have a X capacitor, which increases the differential mode attenuation. Then you have a discharge resistor, which is just for safety. It's meant to make sure that you do not have a lethal voltage on this X capacitor when you disconnect this from the mains voltage. We do have some connectors, different connector options depending on how you choose to connect this to your device. The whole idea with this is to use this when you're prototyping or doing pre-compliance testing in your own lab. You would connect this to your listen and to your device under test. Basically, make sure you have your filter dialed in for exactly the noise that you're dealing with, and then eventually integrate these components onto your circuit board. Common mode choke, which of course has high common mode attenuation and some differential mode attenuation, depending on what part you choose, and Y capacitors, which are also used to attenuate some of that common mode noise to ground, to the protective earth. So the first thing that I do is select the common mode choke, and I used our Red Expert tool, which is online. It's free to use. You just need to log in with your own email address if you want to unlock some of the features. The first thing I'm going to do is look at the common mode graph down here, and I'm going to drag the cursor to 500 kilohertz. So that's the cursor right here. When I do that, it will pop up a new column, common mode attenuation at 500 kilohertz, and then I'll sort that descending. When I sort that descending, you can see a bunch of different part numbers, series, size, inductance, all the different parameters that describe these. I can filter these. In this example, I filtered all the parts that have over 1 amp of rated current, and also all the parts that have less than 15 millimeters of width. And I can add other filters as well, depending on my needs. Once I have most of my constraints added into this tool for the filtering aspect, I can click over here and add a couple of parts. I can add up to 16 parts down into this tray. And then the nice thing about that is I can visually compare the parts looking at the graphs down here. Because even though a part over here might have the best attenuation, I might not look like the look of the graph. So I can visually look at it and compare it to the other ones to make sure I'm choosing the right part. In this case, I chose the part in blue, the 10 millihenry part, because it has the highest attenuation at 500 kilohertz. After I have the common mode choke selected, I calculate the X and Y capacitor values. I calculated those as an X capacitor value of 0.15 microfarad with the part number there, and the Y capacitor value of 2200 picofarad for each one of these Y capacitors. So that's the complete filter. Here I have it simulated in LT Spice. You can see the common mode and the differential mode attenuation. Now let's see how well this works in reality. So when I connect this in front of my device, between the listen and my device, you can see I started out with a crazy amount of noise, 82 dB microvolts before in differential mode. After this graph down here, you can see it knocked this peak down to 43 dB microvolts and also knocked all of these harmonics way down and even lowered the broadband noise down essentially into the noise floor. So for differential mode, this filter did an excellent job. For common mode, you can see the main peak was 70 dB microvolts. After, we did get it down to 46 dB microvolts. And in most of it, we lowered this broadband noise a little bit lower, but you can see here, we still have some work to do because even after this filter, we do have some peaks that are failing or very close to failing. So you can see that even with this approach, we did basically eliminate the differential noise in the conducted band, but the common mode noise, there's still a couple of issues we need to look at, but likely this is all related to the other circuitry on the board and not due to the switching of the FET. So once you're done with conducted emissions, the next step is to do radiated emissions. These are related, believe it or not. So in my experience, I've seen a lot of headaches be removed if you take conducted emissions testing in your own lab, pre-compliance testing done seriously, because a lot of these fundamental frequencies that are down below 30 megahertz will cause issues with harmonics up above 30 megahertz, which is now in the radiated emissions band. Most of these are caused by parasitic capacitances that are on your board from PCB layout, heat sinks, or even the FETs themselves. One of the techniques that I use for getting rid of some of this noise can still be common mode chokes, even though I recommended for them for conducted emissions, especially when you have noise that starts out in the tens of megahertz range in the conducted band. You can have the harmonics filter over into the radiated emissions band. So I generally recommend to start out with a common mode choke for radiated emissions, because most of the noise that's in the radiated emissions spectrum is common mode in my experience. So what core material is best? Manganese zinc is a standard option, which is the graph over here in maroon. Nickel zinc is better if you have higher frequency noise, especially once you get into this 10 megahertz range. That's the line over here in green. If you want the best of both worlds, you can actually choose a product that we have, the WE EXB, and that is both manganese zinc and nickel zinc. And that's this line over here in yellow. And you do get the best attenuation of both of these. If you want even better attenuation than that, nanocrystalline is a good option because it has excellent wideband attenuation, shown by this black line over here, and excellent density. Here is a comparison of a nanocrystalline part compared to a standard manganese zinc part. There's more inductance in the same size because of this higher permeability core material. So for dense designs, which is usually the goal when you're choosing a wide bandgap device, this is something to take into consideration. Some other techniques for passing radiated emissions. Hopefully you're not starting out with something like this, because I don't know if there's much help if this is your design, but you can start out with some shielding materials. We have a ferrite sheet material that you can use. Two main parameters that you would use to choose a ferrite sheet material would be mu prime, and this is for better reflection or redirection of the magnetic field. This is when you're actually using the magnetic field for doing something like wireless charging, NFC, RFID. So the main goal of this is to redirect it to keep this magnetic field away from other circuits, or to redirect it into a certain direction. For example, like NFC and RFID, because then you can actually increase the distance at which you communicate. For mu double prime, that's the other parameter you would look at. This would be used for if you wanted to absorb or eliminate any kind of magnetic field. These would typically be used for attenuating electromagnetic interference. You can use these sheets by putting them on printed circuit board traces in the higher frequencies, like in the gigahertz range. This actually works fairly well. But you can also use these to help minimize reflections inside of a metal enclosure. So even if you have a perfect Faraday box, there's still going to be some resonances, some cavity resonances inside of that box, and you can actually use small sheets of this inside of your box to help eliminate a lot of those reflections. EMI gaskets are also important to consider if you're using a metal box, especially if you're trying to create a complete Faraday cage and you don't have an electrical connection from your lid to your box. You actually have a small gap, even if it's a small microscopic gap that you can barely see between the lid and the box, that will act like a slot antenna and can give you major headaches when you're doing radiated testing. So if you're using a metal box, I highly recommend you look at finding the right EMI gasket that can create a low impedance connection between your lid and your box over wide frequency ranges. If you've done your pre-compliance testing, you might have an EMC compliant device or fairly close to it until you go to the EMC lab and you connect a long cable to it. Then you might have some radiated emissions problems. Of course, with this, you can use cable ferrites to get rid of this noise. In conclusion, wide bandgap devices have lower switching losses that allow for higher power density and higher efficiency. The fast rise times will cause more EMI above 10 megahertz, especially compared to silicon devices, and you will need to mitigate this noise. It's important to have a large toolbox of options because none of these solutions is a magic solution. You'll likely need to use multiple techniques in order to pass EMC. For conducted emissions, like I had talked about, it's mostly differential mode noise, but there is still some common mode noise. LC filters and common mode chokes can be used in the conducted emission band. For radiated emissions, it's mostly common mode noise. You can still use common mode chokes. Of course, use shielding materials, gaskets, and cable ferrites. Even if you have good PCB design, you might still need to use some of these. So if you need help selecting the right component for your EMI problem, please contact your local Wurth Electronics representative. Thank you for your attention.